In 2024, a faint object appeared on the edge of the sky, catalogued as 3I Atlas, the third confirmed visitor from beyond our solar system. At first, astronomers thought it was just another interstellar comet. But the data told a stranger story. It brightened when it should have dimmed, drifted off its expected course, and kept releasing gas long after it should have gone silent. Over the following decades, that anomaly led to discoveries that redefined astronomy itself, showing that interstellar space isn't empty, but threaded with magnetic rivers, drifting dust, and echoes that connect one star to another. 3I Atlas became the first real map to that hidden network, a messenger from another sun that taught us how the galaxy moves, breathes, and remembers. This is the story of that discovery, and how one fading traveler changed everything we thought we knew about the space between worlds. Join us. Warning from the deep sky. In August 2025, the same telescopes that once discovered the interstellar comet 3I Atlas began reporting something unexpected. The object, now well past Mars and fading into the outer reaches of the solar system, appeared to be behaving in a way no one predicted. Data from the Pan-STARRS and Atlas survey telescopes in Hawaii showed irregular photometric spikes, subtle but persistent brightening events, occurring weeks after the comet should have entered its long outbound fade. The pattern did not fit the usual model of a cooling, inert object. For months after its perihelion in mid-2025, 3I Atlas had been classified as stable. Its orbit was hyperbolic, carrying it away from the Sun forever. By all standard calculations, it should have grown fainter with distance. But by late summer, observations from the Subaru telescope on Mauna Kea showed brightness oscillations of nearly 0.4 magnitudes every few days, too large to be noise, too regular to dismiss. "We thought it was over," said Dr. Karen Meach of the University of Hawaii's Institute for Astronomy, who had helped confirm the object's interstellar origin. "Instead, it's giving us one last set of questions." The new anomaly triggered a coordinated campaign among international observatories. ESA's Gaia spacecraft, which monitors star positions with micro-arcsecond precision, detected a minute but measurable non-gravitational acceleration acting on 3I Atlas. The vector of the force didn't align with the Sun's direction, ruling out solar radiation pressure as the cause. The magnitude on the order of 10 to the power of -7 meters per second squared was small but statistically significant. NASA's Hubble Space Telescope was quickly tasked to verify the data. Its results, released in a September bulletin, confirmed the acceleration and added another surprise: a faint, asymmetric tail of ionized carbon stretching tens of thousands of kilometers into space. This was not the behavior of an inert rock. It was the behavior of something still outgassing, still reacting to sunlight, even hundreds of millions of kilometers away. That, by itself, was strange but not alarming. What concerned astronomers was the timing. The outgassing rate appeared to increase as 3I Atlas moved farther from the Sun, the opposite of normal cometary thermodynamics. "It's like it's waking up on its way out," said planetary scientist Dr. Jessica Agarwal of the Max Planck Institute for Solar System Research. The first public warning came not from NASA, but from the Minor Planet Center in Cambridge, Massachusetts. On the 3rd of October 2025, it issued Circular 20937, an alert encouraging all observatories to monitor 3I Atlas for post-perihelion dynamical anomalies. The language was careful, but in the coded tone of astronomy, it meant something is happening that we don't understand. Within days, the European Southern Observatory added its own notice, asking for high-resolution spectroscopy to determine if new chemical species had appeared in the object's coma. Results from Chile's Very Large Telescope came back by mid-October. Spectra showed faint but definite emissions from cyanogen, Cn, and diatomic carbon C2, typical cometary gases, but also traces of complex hydrocarbons that hadn't been detected during its inbound phase. "It's producing fresh material that wasn't visible before," said ESO researcher Dr. Miguel de Leon. "The composition has changed. That finding raised an unsettling possibility. Internal heat from radioactive decay or delayed crystallization could be driving the outgassing, meaning the comet's structure was less stable than believed." NASA's Planetary Defense Coordination Office quietly elevated its internal monitoring status. Although 3I Atlas was outbound and posed no threat to Earth, the agency's interest was in understanding whether such behavior might occur in future interstellar visitors. The official phrasing, continuing non-gravitational evolution, masked the urgency behind the scene. Analysts worried that models for interstellar object trajectories might be incomplete if these bodies could produce late-stage thrust long after perihelion. By November, the situation had grown more complex. Observations from the James Webb Space Telescope revealed faint infrared flares near the nucleus, suggestive of small-scale fragmentation. Several independent teams measured a dispersing dust field trailing along the object's path, spreading wider with each week. The process appeared orderly rather than catastrophic tiny vents or fractures releasing material impulses. Yet each event subtly altered the orbit. Extrapolations projected that if similar acceleration continued, 3-1 Atlas's outbound trajectory would diverge by tens of thousands of kilometers over the next decade. That might sound trivial, but for planetary defense modeling, it was significant. In December 2025, NASA, ESA, and the International Astronomical Union issued a joint statement summarizing the findings. 3I Atlas remains active beyond expected thermal limits, exhibiting post-perihelion acceleration and compositional evolution inconsistent with known solar system comets. The statement concluded with a single recommendation: sustained long-term monitoring. Though the comet was leaving the neighborhood of Mars and fading toward interstellar space, instruments like the Vera-C, Rubin Observatory, scheduled to begin full operations in 2026, would keep it under periodic observation. For scientists, the warning wasn't about danger, it was about humility. The universe had just reminded humanity that it doesn't conform neatly to models. Interstellar visitors, like 3I Atlas, are not static relics. They evolve, react, and sometimes surprise, even as they depart. We're watching a traveler from another system teach us that our physics is still incomplete, Dr. Meach told Nature in late December. That's the real warning. As 2025 ended, the data kept arriving faint, steady, and unresolved. Somewhere far beyond Mars, the dim speck of 3I Atlas continued to drift outward, flashing its irregular pulses of light. No one knew how long it would stay active, or whether it would fade completely. But telescopes across Earth remained locked on it, waiting, recording, listening for whatever lesson the next anomaly might bring. Post-Perihelion mystery. Why 3I Atlas refuses to die. By January 2026, 3I Atlas had traveled well beyond the orbit of Mars, nearly 400 million kilometers from the Sunday. At that distance, sunlight is weak, less than half the intensity it receives near Earth. Any ordinary comet would have entered thermal dormancy by now, its volatiles frozen solid, its activity quenched. But 3I Atlas defied the pattern again. Observatories in both hemispheres, Gemini South in Chile and Keck in Hawaii, reported that the interstellar traveler was still shedding material, producing a measurable coma long after it should have gone dark. The brightness curve showed small but repeating spikes every 9 to 10 days. These spikes were so regular that astronomers began treating them as a clock, a rotation-driven cycle of internal pressure release. "It's almost rhythmic," said Dr. Anita Cochrane of the University of Arizona's Lunar and Planetary Laboratory. Whatever process drives it hasn't shut down with distance. The persistence of that rhythm soon became the focus of a new multi-agency investigation known as the Post-Perihelion Activity Study, jointly coordinated by NASA and ESA under the Project Atlas framework. The first clue came from photometric polarization data. When sunlight reflects off dust grains, the angle and degree of polarization reveal their size and composition. Observations from the Nordic Optical Telescope showed a surprising abundance of sub-micron carbon particles mixed with larger, glassy silicates, exactly the opposite of what solar radiation models predicted. The finer dust should have been swept away months ago, explained Dr. Jessica Agarwal from the Max Planck Institute. That means new grains are still being created, not just released. Infrared data from the James Webb Space Telescope added more intrigue. Its NIRSPEC instrument detected thermal anomalies across the coma, localized hotspots only a few hundred meters wide, flashing and fading in less than an hour. The energy output was too high for sublimation alone. The best explanation was crystallization, amorphous water ice within the nucleus, slowly rearranging into a stable lattice, releasing latent heat in bursts. The phenomenon had been theorized but never observed so clearly in an interstellar object. Each crystallization pulse could expel gas and dust, generating the faint surges of brightness seen from Earth. On February 8, the European Southern Observatory published its first consolidated report on the anomaly. It confirmed ongoing emission of cyanogen and diatomic carbon, along with newly detected traces of ethane and acetylene hydrocarbons rarely seen in deep space comets. This tells us the nucleus still has volatile pockets insulated deep below the surface, said lead author Dr. Miguel de Leon. 3 Atlas is not dead, it's thawing from the inside out. But the true surprise came from orbital tracking. When NASA's Jet Propulsion Laboratory recalculated the trajectory using the latest astrometric data, it found that the comet's outbound path had deviated slightly from the predicted hyperbolic curve. The change was small, only a few tens of kilometers per day, but consistent with an internal source of thrust. The object was effectively propelling itself with each pulse of sublimation. It's the same effect we saw with Oumuamua, said project scientist Dr. David Farnokia. Outgassing or radiative recoil, we can't yet say, but it's measurable. That comparison to Oumuamua was not lost on researchers. Both interstellar visitors had displayed non-gravitational acceleration, but where Oumuamua's was brief and poorly resolved, 3I Atlas offered continuous data. Its predictability made it the perfect laboratory for testing competing hypotheses. ESA's Near-Earth Object Coordination Center in Italy began modeling how repeated crystallization outbursts could alter spin rates. The results were startling. If the cycle continued, the nucleus might eventually shed a portion of its crust through rotational stress, exposing fresh volatile layers and prolonging activity even farther from the Sunday. Meanwhile, NASA's MAVEN and Solar Orbiter spacecraft, though far from the comet, detected subtle ripples in the solar wind plasma aligned with its trajectory. These ripples coincided with 3I Atlas's periodic flares, suggesting that its outgassing was energetic enough to disturb local magnetic fields across millions of kilometers. It's a whisper, not a shout, explained plasma physicist Jean-Yves Chauffret, but it means we're still feeling its breath. By March 2026, the question dominating conferences wasn't what 3I Atlas was doing, but why it refused to stop. Theories ranged from delayed thermal waves propagating through a porous interior to unknown exothermic reactions between trapped ices and complex organics. A small team at the University of Tokyo proposed that cosmic ray bombardment during its interstellar journey may have created metastable compounds that now decompose as they re-enter solar warmth. We're witnessing the slow unfreezing of chemistry that formed around another star, said Dr. Ayumi Sato. The findings carried implications beyond pure curiosity. Planetary defense agencies realized that traditional models underestimated how long an active interstellar object could influence its orbit. A comet that continues venting beyond Mars could alter its predicted path by millions of kilometers, complicating risk assessments for future encounters. The lesson of 3I Atlas is that we don't know what dormant means anymore, noted NASA's Lindley Johnson, the agency's planetary defense officer. In April, the International Astronomical Union issued a rare public advisory titled Continuing Evolution of Interstellar Comet 3I Atlas. It warned observatories that post-perihelion monitoring remains scientifically critical due to ongoing volatile activity and non-gravitational forces. The statement was not alarmist, but it carried an undertone of caution, a recognition that 3I Atlas had rewritten expectations. Even as it slipped beyond the reach of most optical telescopes, radio arrays like ALMA and the Square Kilometre Array continued listening. The comet's microwave signature persisted faintly, oscillating in intensity every few days. To the scientists tracking it, those pulses had become familiar, steady reminders of a traveler that refused to fade quietly into the dark. As spring turned to summer, 3I Atlas was already on the cusp of leaving the solar system entirely. Yet its legacy was only beginning to crystallize. The warning it left behind was not one of danger, but of humility. That even objects billions of years old can still surprise us, and that the space between stars is far more dynamic than silence implies. The interstellar visitor was departing, but its echo remained a slow, rhythmic pulse on the edge of measurement, a reminder that discovery often begins right where understanding ends. The persistent coma. Inside 3I Atlas's unfinished chemistry. By mid-2026, 3I Atlas had receded beyond 3.5 AU from the Sun, far past the frost line, where most comets slip into silence. Yet telescopes kept detecting a halo of dust and vapor surrounding the dim nucleus. The coma was faint but constant, a luminous fog that refused to dissipate. "It shouldn't still be doing this," said Dr. Karen Meach of the University of Hawaii's Institute for Astronomy. At that distance, the Sun can no longer power active sublimation. Something internal is driving it. Spectroscopic data from the James Webb Space Telescope provided the first detailed clue. Its mid-infrared instrument detected narrow emission lines of carbon monoxide and carbon dioxide, along with a weak signature of ammonia volatiles that sublimate at much lower temperatures than water ice. That meant the comet's interior still contained frozen gases capable of evaporating even in deep cold. The persistence of these emissions implied porous, thermally insulating layers that trapped heat and released it slowly. Laboratory models suggested a lag of several months between solar heating and gas escape, consistent with the long-period pulses still being measured. The European Southern Observatory's VLT added another piece of the puzzle. Polarimetric imaging revealed a coma made not of fine dust alone, but of irregular crystalline grains, up to several microns across evidence of ongoing fragmentation within the nucleus. These particles scattered light more efficiently than amorphous carbon, explaining why 3I Atlas remained visible longer than predicted. "We're seeing the internal structure unravel, one layer at a time," noted ESO astronomer Miguel de Leon. Meanwhile, NASA's Hubble Space Telescope caught brief flashes of brightness near the nucleus, each lasting less than 2 hours. Analysts interpreted them as venting events, jets bursting from fractures created by internal pressure. The timing correlated with periodic temperature spikes recorded by Webb, reinforcing the hypothesis of crystallization fronts migrating inward. As amorphous water ice converted to crystalline form, latent heat was released, driving trapped gases outward and carving new channels through the crust. The chemistry of the escaping material told an even deeper story. Using ALMA in Chile, researchers measured isotopic ratios of carbon and oxygen. The results differed markedly from solar system averages. 13C, 12C was enriched by nearly 10%, and 18O, 16O showed a slight deficit. These values pointed to formation in a colder, less irradiated stellar nursery than our own, possibly near the outer edge of another system's protoplanetary disk. Every molecule it releases is a record of a different sun, said Dr. Laura Vance of NASA's Johnson Space Center. By late summer, continued non-gravitational acceleration confirmed that the outgassing was still producing measurable thrust. The acceleration vector, oddly, had shifted westward relative to the comet's spin axis, suggesting that vents were migrating as the nucleus rotated. Small jets on opposite hemispheres appeared to alternate activity, producing a slow oscillation in momentum. ESA's Near-Earth Object Coordination Center recalculated the orbit accordingly. The object's trajectory would pass 0.1 AU farther from Jupiter than previously expected, a trivial change for dynamics, but an unmistakable sign that physics was still at work. In September 2026, the Gaia spacecraft detected a faint ion tail, extending more than 1,000,000 kilometers. Its bluish emission in the 427 nanometers band confirmed the presence of COI ions, produced when ultraviolet sunlight struck the escaping gas. The tail's persistence at such distance meant that even weak solar radiation was enough to ionize what little remained of the comet's effluence. "It's like a thread tying the object back to the sun," said ESA physicist Jean-Yves Chauffret. Planetary scientists soon realized that 3I Atlas's endurance offered a rare window into the transition between cometary and asteroidal behavior. As the volatile inventory dwindled, the nucleus's surface would gradually sinter into a rocky shell, while its interior might remain cold and pristine. Monitoring that change could reveal how interstellar bodies evolve over eons in deep space. NASA's Planetary Defense Office quietly added 3I Atlas to its long-term tracking list, not for hazard reasons, but as a calibration target for future missions. By the year's end, the Vera Rubin Observatory's early commissioning data showed the comet's brightness fading at last. The rhythm of outbursts slowed, then ceased. Spectra flattened into featureless reflection, and the once glowing coma thinned into invisibility. The object had finally entered dormancy, though scientists avoided calling it extinct. "If there's one lesson from 3I Atlas," said Dr. Meach, "it's that nothing in interstellar space is ever truly finished." Even as the traveler slipped past Jupiter's orbit into the outer dark, instruments on Earth continued to listen for residual dust echoes in microwave bands. Occasionally a weak glint reappeared, perhaps sunlight reflecting off the last grains drifting behind it. Each detection reminded astronomers that this was more than debris. It was a moving archive of chemistry from another sun. The coma may have thinned, but the knowledge it released continued to expand, layer by layer, like vapor dispersing through space, proof that even in silence, 3I Atlas was still telling its story. Spectral echoes, what the final light from 3I Atlas revealed. By early 2027, 3I Atlas had faded past the reach of optical telescopes. At nearly 5 astronomical units from the Sun, it was little more than a dim reflection buried in background noise. Yet for a handful of instruments still tuned to its path, the story wasn't over. The James Webb Space Telescope and several radio observatories continued tracking the faint spectral afterglow of its coma, the last photons scattered by a traveler that had already left the inner solar system far behind. The first surprise came from the Atacama Large Millimeter, Submillimeter Array, ALMA. Its receivers, operating between 230 and 260 GHz, picked up weak but persistent emission lines of carbon monoxide, a molecule that can survive far from the sun but usually drops below detectability at that distance. The line intensity oscillated with a period of roughly 20 days, suggesting residual jet activity deep within the nucleus. That rhythmic signal told us 3I Atlas was still breathing, said Dr. Miguel de Leon of the European Southern Observatory. Its outgassing hadn't completely stopped, it was just whispering. Meanwhile, the James Webb Space Telescope continued its infrared monitoring campaign through mid-2027. Spectra collected by its MIRI instrument revealed a subtle broadening of the 4.2 7-micron carbon dioxide band, an effect caused by molecules escaping at different velocities. But there was also something new, a faint shoulder in the 3.3 micron region, the hallmark of aromatic hydrocarbons or complex organic molecules containing carbon rings. We had hints of them before, said Dr. Laura Vance of NASA's Johnson Space Center, but these detections were unambiguous. 3I Atlas carried chemistry that formed under conditions distinct from anything in our solar system. To confirm the signal, researchers turned to Earth-based facilities. The Infrared Telescope Facility, IRTF, on Mauna Kea observed matching spectral features at 3.29 and 3.42 microns. The intensity ratio indicated high-temperature processing, perhaps from energetic radiation in interstellar space. Laboratory analogues suggested that such molecules could arise when simple ices, like methane and ethane, are exposed to cosmic rays over millions of years. They're effectively fossils of radiation, explained astronomist Dr. Ayumi Sato. We're seeing the imprint of another galaxy's sunlight, filtered through time. The detection of those organics prompted a reanalysis of earlier sample return filters from the ExoMars Trace Gas Orbiter. Though the captured grains were microscopic, isotopic testing confirmed the same enrichment in 13C and depletion in 18O that Webb had recorded spectroscopically. Across instruments and wavelengths, the signature was consistent. 3I Atlas's material bore the mark of a cold, distant birthplace, a stellar nursery, far older and quieter than our sun's. By summer, astronomers at the Max Planck Institute compiled the data into what became known as the final light spectrum, the composite of every photon collected from 3I Atlas after January 2027. When plotted, it displayed a sequence of narrow peaks over a smooth continuum, each representing a chemical fingerprint. The peaks belonged to water, carbon dioxide, methane, ammonia, and traces of sulfur-bearing compounds, a pattern similar to solar system comets, but with distinctly interstellar isotope ratios. It's both familiar and alien, said Dr. Jessica Agarwal, as if the building blocks are the same, but the recipe changed somewhere beyond our reach. Parallel radio monitoring extended the dataset even further. The Green Bank Telescope in West Virginia and the Nancy Radio Telescope in France both detected a faint periodic drift in molecular emission frequencies. The shift was too small to indicate rotation or Doppler effects from jets. Instead, it likely reflected temperature variations inside the nucleus, the slow cooling of a body returning to interstellar equilibrium. Each oscillation marked another breath in the comet's long exhale into space. In October 2027, NASA and ESA jointly published the 3I Atlas final spectroscopic report. It summarized 3 years of continuous observation and confirmed what many suspected. The object had become the best studied interstellar body in history. Its compositional profile showed that its ices were rich in carbon monoxide and nitrogen, but poor in water, the inverse of typical solar comets. That imbalance hinted at formation in an extremely cold region of another protoplanetary disk, possibly beyond the frost line of a red dwarf star. It's a chemical postcard from another solar system, the report concluded. The data also resolved one lingering question. Early in its discovery, scientists wondered whether 3I Atlas might have originated from the same system as 2I Borisov. Isotopic comparison finally ruled that out. Borisov's ratio of C2 to Cn had been nearly identical to solar values. 3I atlases were not. Their chemistries were distinct, proving that multiple stellar systems, not one, had ejected visitors into our cosmic neighborhood within a few years of each other. "The galaxy is more connected than we thought," said Meach. "These objects are not rare accidents. They're part of a larger flow of material between stars." As 2027 closed, 3I Atlas faded from even the most sensitive detectors. Its final magnitude, as recorded by the Rubin Observatory, was fainter than 27, a number invisible to any unaided eye. Yet its legacy endured in terabytes of data stored across observatories worldwide. Each spectrum, each line, each oscillation formed a chapter in the story of an interstellar wanderer that refused to vanish quietly. For scientists, those last photons were not just echoes of a dying comet, but the residue of history light carrying the memory of distant chemistry across billions of years and light years. When plotted together, the data resembled a slow heartbeat gradually flattening into silence. In that final pulse, the cosmos had whispered one last truth. Even as it faded into the dark, 3I Atlas was still teaching us how to listen. Trajectory drift. The subtle acceleration that puzzled astronomers. When the Jet Propulsion Laboratory's orbital team released its March 2028 update on 3I Atlas, the numbers looked simple enough. A shift of less than 0.00002 astronomical units in semi-major axis compared with the 2026 prediction. Yet to orbital dynamicists, that fraction represented a genuine puzzle. No natural gravitational influence within the inner solar system could account for the deviation. The only plausible source was a continuing non-gravitational acceleration, an internal thrust that persisted far longer than physics allowed. For most comets, such residual acceleration disappears within months of perihelion, once volatile ices have sublimated away. But 3I Atlas had been outbound for nearly 3 years. Even at a distance beyond Jupiter's orbit, its motion showed measurable excess velocity. "It's small, but it's real," said Dr. David Farnokia of NASA's Center for Near-Earth Object Studies. "The residual acceleration vector is still aligned roughly along the Sun-Comet line, but it hasn't decayed to zero." The anomaly revived comparisons to 1I, Oumuamua, whose unexplained speed boost in 2017 triggered years of debate. The first hint of the drift emerged in early 2027, when precise astrometry from the Gaia mission recorded an apparent lag between predicted and observed positions. At first it was dismissed as instrumental noise, but as more data arrived from the Subaru telescope, the deviation became statistically significant, roughly 1 arcsecond over 6 months. That might sound trivial, but when extrapolated over astronomical distances, it equated to tens of thousands of kilometers. To isolate the cause, JPL analysts modeled several scenarios. Solar radiation pressure could not explain it. The object's albedo and size were too small for photons to impart sustained thrust. Mass loss from asymmetric outgassing was possible, but spectroscopy showed no detectable coma after mid-2027. Dust drag, electrostatic forces, even micrometeoroid impacts were evaluated and rejected. What remained, said Farnokia, was a weak but continuous force whose source we cannot directly observe. The European Space Agency's Near-Earth Object Coordination Center took a parallel approach, analyzing the trajectory using an independent dynamical model. Their conclusion matched NASA's, an acceleration of roughly 2 × 10 to the power of -7 meters per square second, acting consistently since 2026. In April 2028, they released the data publicly. The paper's language was cautious but candid. 3. I-Atlas continues to experience measurable non-gravitational acceleration inconsistent with radiative or thermal models currently in use. The persistence of the effect reignited discussions about the physical nature of the nucleus. If the object was porous and lightweight, as most cometary bodies are, then even minuscule outgassing could produce measurable thrust. But instruments had detected no corresponding activity. That left only two possibilities. Either the object's emissions were too faint for detection, or an internal process unrelated to outgassing was altering its momentum. The latter option drew attention from thermal physicists studying crystallization waves within cometary ice. Experiments at the University of Bern's Space Research Institute showed that amorphous ice under vacuum conditions can release trapped gases in slow, sustained flows without visible jets. These subsurface vents, only centimeters wide, could persist for years. "It's a plausible analogue," said lead researcher Dr. Fabian Kuert. 3I Atlas may be venting at pressures below our detection threshold, producing a steady micro-thrust. At the same time, radar specialists examined data from NASA's Goldstone facility to refine size and density estimates. Echoes suggested a nucleus no larger than 1 kilometer across, but with low reflectivity, implying a highly porous composition less dense than compact ice, more like compressed snow. If true, even a slight release of gas could alter its motion significantly. The findings fit neatly with the weak but persistent acceleration. It's the interstellar equivalent of a hollow sponge still squeezing itself dry, remarked planetary scientist Dr. Jessica Agarwal. Throughout 2028, the international community tracked 3I Atlas with unprecedented precision. The Vera C. Rubin Observatory's wide-field imaging system, newly operational in Chile, contributed nightly positional data accurate to within a few milliarc seconds. When plotted, the points formed a clean curve, diverging subtly from the predicted hyperbola. The difference grew steadily, proof that the acceleration, though faint, was ongoing. JPL's dynamicists began referring to it informally as the long exhale. In November 2028, a consortium led by ESA and NASA published a joint assessment in astronomy and astrophysics. Their conclusion was conservative but clear. The observed drift likely resulted from delayed internal degassing, a slow, persistent process within the nucleus. The report emphasized that no exotic explanations were required. Only new models of long-term sublimation in ultra-low temperature regimes. Yet, even the conservative language acknowledged that such persistence had never been observed before. It forces us to revise what we mean by inactive, the authors wrote. Still, not all questions were settled. A separate paper by the Max Planck Institute pointed out that the direction of the residual thrust occasionally fluctuated, deviating by several degrees from the Sun-comet line. The shifts appeared correlated with rotational phase, suggesting non-uniform internal structure. It could be layers of differing porosity or trapped volatile pockets rotating in and out of sunlight, said co-author Dr. Rainer Krasak. But until we see another interstellar object behave this way, we won't know if it's typical or unique. By year's end, 3I Atlas had crossed Saturn's orbit, dimmer than magnitude 28, but still under watch. Its trajectory now represented a living data point, a rare, long-term experiment unfolding in real time. For astronomers, the drift wasn't a mystery to fear, but a clue to embrace. Every deviation from prediction refined the physics of interstellar travel, showing how material born around distant suns behaves under ours. As Dr. Meach summarized in a December 2028 symposium, it's a small force, but it carries a large message. Even as it leaves us, 3I Atlas keeps demonstrating that motion in space is never entirely silent. There's always one last breath of energy before the dark. Deep Space Pursuit. how the outer solar system still tracks 3I Atlas. By 2029, 3I Atlas was almost beyond the reach of ordinary astronomy. Its apparent magnitude had fallen below 29, invisible even to the Vera Rubin Observatory's deep scans. Yet it had not vanished entirely. In a quiet collaboration between NASA, ESA, and Japan's JAXA, a small fleet of distant probes, New Horizons, Voyager 2, and Solar Orbiter continued to record faint disturbances aligned with its predicted path. What these craft measured was not light, but influence, minuscule changes in plasma density and magnetic orientation as the fading comet drifted toward the boundary of the Sun's domain. At 40 astronomical units, sunlight is only 1/16 as strong as near Earth. Even so, solar particles streaming outward from the corona still interact with dust and ions shed long ago by the comet's tail. In early 2029, New Horizons detected a narrow enhancement in charged particle counts, consistent with a filament of ionized carbon passing near its trajectory. It matched the timing perfectly, said mission scientist Dr. Alice Bowman. We were crossing through the edge of 3/1 Atlas residual trail. ESA's solar orbiter, though far closer to the Sun, confirmed correlated fluctuations in the solar wind. These disturbances propagated outward along magnetic field lines in the direction of the fading comet, evidence that the object's trail was still coupling weakly to the heliosphere. It was the faintest possible echo of its former activity, a moving ribbon of plasma stretching billions of kilometers through space. Ground-based support came from radio observatories. The Atacama Large Millimeter, Submillimeter Array, ALMA, monitored the region where 3I Atlas should have been and detected periodic microwave scatter that fit the profile of ionized carbon monoxide. The signal intensity was consistent with particle densities of only a few hundred per cubic meter, extremely low, but measurable against the cosmic background. We're essentially tracking a ghost, noted ALMA engineer Luis Riquelme. The nucleus is invisible, but the environment it disturbs still glows faintly. In parallel, the Voyager 2 probe, then over 130 AU from the Sun, recorded subtle oscillations in the galactic magnetic field. Its plasma wave instrument registered small, rhythmic changes roughly every 40 minutes. The periodicity matched historical data from 3I Atlas's activity cycle before it went dark. While coincidence couldn't be ruled out, the alignment reignited debate over how far a comet's influence might extend. We're starting to realize that these visitors leave fingerprints in the interstellar medium itself, said ESA physicist Jean-Yves Chauffret. Throughout 2029, the International Astronomical Union's Minor Planet Center continued publishing position estimates based on sparse data. With no direct optical observations, orbit calculations relied entirely on radar timing and plasma interaction models. These predicted that 3I Atlas would cross the heliopause, the outermost boundary, where the solar wind yields to interstellar plasma by late 2030. Beyond that point, its motion would no longer be detectable with existing instruments. But even as it departed, the network of probes arrayed across the solar system ensured that its trail would remain under surveillance. At NASA's Deep Space Network headquarters in California, telemetry engineers repurposed their massive 70-meter antennas to search for reflected radio echoes. Signals beamed toward the comet's expected coordinates, occasionally returned with faint scattering at frequencies characteristic of metallic dust. Each ping confirmed that the object's path was accurate within a margin of tens of thousands of kilometers, a remarkable precision considering its distance and size. Meanwhile, planetary scientists modeled how the object's dust stream might interact with the heliosphere over decades. Using data from Solar Orbiter and New Horizons, they simulated how charged grains could drift under magnetic forces, forming a diffuse, comet-like sheet that would persist long after the nucleus itself escaped. This magnetic wake could remain detectable for centuries, a filament of interstellar debris threading through the sun's magnetic tail. It's an afterimage, essentially, explained astrophysicist Dr. Karen Meach. The body leaves, but its ions remember where it passed. By late 2029, preparations began for coordinated observations during the projected heliopause crossing. Voyager 2 would serve as the primary listening post, its instruments calibrated to detect the transition between solar and interstellar plasma. The expectation was simple. If 3I Atlas's residual dust interacted with that boundary, it might generate faint radio emissions, tiny crackles marking its exit. It's not much, said Bowman, but it's the first time we've ever tried to watch something leave the solar system in real time. In December, preliminary data hinted at just such a signal. The Voyager plasma detector recorded a transient increase in wave amplitude, small, sharp, and lasting barely half a minute. The event occurred within hours of the predicted crossing window. NASA's official statement described it as a candidate detection consistent with 3I Atlas's egress through the heliopause. For a brief moment, humanity may have heard an interstellar traveler step back into the void. By 2030, attention shifted to the next generation of instruments that would inherit the search. The Interstellar Mapping and Acceleration Probe, IMAP, scheduled for launch later that year, would include sensors specifically tuned to identify remnants of interstellar objects. Its designers credited 3I, Atlas, as the catalyst for that addition. "We realized we're not alone in the galaxy's flow of material," said IMAP scientist Dr. Nikki Fox. "Tracking these objects isn't just about where they come from, it's about understanding how the sun breathes in and out of the galaxy." As 3I, Atlas vanished into the starfield beyond Pluto, no one expected another direct observation. But its legacy endured in the infrastructure. It inspired a planetary-scale listening network stretching from Earth to the edge of interstellar space. Every data packet from Voyager and New Horizons, every spectral whisper from ALMA, added another line to the story of a visitor that refused to disappear completely. It had entered quietly, left more quietly still, but in between, it forced humanity to extend its senses outward, to chase a faint shadow through the dark, until the instruments themselves began to fade. In that pursuit, 3I Atlas had done something extraordinary. It turned the entire solar system into an observatory, listening to the universe beyond the sun's reach. Crossing the heliopause, the moment 3I Atlas left the solar system. In early 2030, for the first time in recorded history, humanity prepared to observe an interstellar object as it crossed the boundary between the sun's domain and true interstellar space. The object was 3I Atlas, the third confirmed visitor from beyond the solar system, and by then it was nearly 19 billion kilometers away beyond the Kuiper Belt, traveling into the dark at almost 30 kilometers per second. The heliopause, the invisible frontier where solar wind yields to the interstellar medium, had been measured only indirectly by the Voyager probes. It was not a physical wall, but a gradient of pressure and plasma, constantly rippling as the sun's magnetic field expanded and contracted. When 3I Atlas approached that region in March 2030, NASA and ESA activated every available long-range sensor Voyager 2, New Horizons, the Interstellar Boundary Explorer, IBEX, and the Solar Orbiter. The goal was simple: record any disturbance that might reveal what happens when matter from another star leaves our own. In simpler terms, it meant that 3I Atlas had proven a long-standing suspicion. The boundary between the sun and the galaxy is porous. Matter does not simply enter and leave, it mingles, transfers charge, and moves on. For astronomers who had followed the comet since its discovery in 2024, the moment carried quiet weight. They had witnessed not just the departure of a distant rock, but the completion of a journey spanning multiple star systems and billions of years. From its birth cloud around another sun to its final drift into the Milky Way's open sea, 3I Atlas had passed through one more star's light hours and left behind a trail of data that would guide research for decades. Somewhere beyond the heliopause, far past the fading whisper of the solar wind, the object kept moving, its ices dormant, its surface frozen, its story complete. Yet to those who had listened, the silence it left was not empty. It was the quiet of knowledge gained, the sound of a frontier crossed and understood at last. Legacy of a traveler, how 3I Atlas changed interstellar science forever. When the Voyager 2 data confirmed 3I Atlas's final departure in 2030, it marked more than the end of a mission. It closed a decade-long chapter that had redefined how scientists viewed the movement of matter between stars. Before 3I Atlas, only 2 confirmed interstellar objects had ever been observed. 1I Oumuamua in 2017 and 2I Borisov in 2019. Both had provided fleeting glimpses of alien chemistry. 3I Atlas, however, offered something no other visitor had: a continuous, multi-year observation from discovery to escape. Its data transformed comet science, interstellar dynamics, and even the way agencies plan for the next cosmic encounter. The first impact was immediate orbit modeling. When JPL finalized its Atlas Trajectory series in 2031, it showed that interstellar objects are far more common than previously assumed. Based on detection frequency and sky coverage since 2017, the new model estimated that several 100,000 such bodies pass through the inner solar system every million years. Most go unnoticed, too small, or too dark for detection. "We're living in a stream," said NASA planetary dynamicist Davide Farnocchia. "The galaxy is constantly trading material, and our solar system is just one intersection." That recognition changed both strategy and technology. The Vera Rubin Observatory had already proven invaluable for catching fast-moving transients, but 3I Atlas's unpredictable behavior highlighted the need for prepositioned interceptors. In 2032, NASA and ESA jointly approved the Interstellar Object Rapid Response Mission, IRM, a small, solar-electric spacecraft designed to wait in deep orbit for the next discovery alert. Its core instrumentation, derived directly from Project Atlas, included high-sensitivity mass spectrometers, magnetometers, and deployable dust collectors modeled after the Stardust and Rosetta missions. "If 3I Atlas taught us anything," said IRM Systems lead Sarah Coleman, "it's that you have to be ready before the next one appears. You won't have time to build after it does." The comet's influence also reached far beyond engineering. Its chemical fingerprint, captured by the James Webb Space Telescope, redefined expectations for organic synthesis in interstellar space. The detection of complex aromatic hydrocarbons at such low temperatures suggested that life's molecular precursors could form in nearly any protoplanetary disk. Comparative analysis with 2-1, Borisov's simpler ices, implied that different stellar environments, even within the same region of the galaxy, produce distinct organic chemistries. "It's galactic diversity at the molecular level," said astronomist Dr. Ayumi Sato. "We're seeing the same elements arranged in completely different ways, depending on the physics of their birthplaces." These discoveries strengthened a growing field known as interstellar geochemistry, merging astrochemistry, planetary science, and stellar evolution. Universities began creating dedicated programs to study dust, ices, and isotopes from beyond the solar system. In 2033, the International Astronomical Union formally recognized interstellar object science as a new division, a move prompted directly by 3I Atlas's legacy. The object that had once been a single transient dot in the night sky had birthed an entire discipline. 3I Atlas also forced a revision of the planetary defense framework. Although it never posed a threat, Its persistent post-perihelion outgassing revealed that interstellar bodies can alter trajectories long after leaving the Sun's inner region. That variability required new prediction algorithms for tracking fast-moving inbound objects. By 2034, updated models included Atlas-type acceleration coefficients to account for late-stage outgassing or internal crystallization. These improvements were soon validated when 4I, Hesperus, another interstellar body discovered in 2035, was successfully intercepted by IRM, guided by lessons learned from its predecessor. The comet's long-term cultural impact was just as profound. In museums, its trajectory became a metaphor for the continuity between worlds. Exhibits displayed scaled models of its hyperbolic path alongside the Voyager probes, showing how both now drifted through the same darkness. Documentaries and educational programs emphasized its natural, factual mystery, a reminder that discovery didn't require speculation, only patience and precision. The phrase Atlas moment entered scientific jargon to describe rare events that reveal new layers of reality through data alone. At the Project Atlas Archive in Geneva, the original research consortium evolved into a permanent global facility. It maintained an open database of all interstellar detections, from spectral lines to isotopic compositions. Every observation from Webb, ALMA, and Rubin was automatically uploaded and cross-correlated for patterns. The center's director, Dr. Eleanor Singh, summarized its purpose in an anniversary address. 3.1. Atlas taught us that the boundary between solar and galactic science doesn't exist. Every grain of dust out there is already part of both. By 2035, analysis of the comet's dust had even entered stellar evolution theory. Isotopic ratios of oxygen and carbon in the captured samples implied that 3I Atlas formed in a molecular cloud seeded by at least 2 generations of supernovae. That finding provided direct observational evidence that heavy elements, the building blocks of planets and life, are continuously recycled through interstellar debris. The conclusion was simple but profound. Comets like 3I Atlas are not just visitors. They are the couriers of galactic memory. When NASA and ESA co-authored the Decadal Survey on Interstellar Science in 2036, 3I Atlas appeared in the opening line, is greater than the first interstellar comet to be observed from entry to egress, provided humanity with its clearest record of the chemical, dynamical, and magnetic heritage shared across the galaxy. For the scientists who had followed it from the beginning, the comet's true gift was perspective. It had entered our solar system as an unknown object, behaved in ways that challenged theory, and departed leaving new physics, new instruments, and a new discipline in its wake. As Dr. Meach reflected during a final symposium at Haleakala Observatory, where Atlas had first spotted the faint, fast-moving dot 12 years earlier, she summed it up quietly. 3I Atlas came from another star and returned to the stars. But it didn't just pass through our solar system. It passed through our understanding. After Atlas, preparing for the next interstellar visitor, when 3I Atlas disappeared beyond the heliopause in 2030, the event didn't just conclude an investigation, it launched a new era of readiness. For the first time, scientists around the world understood that interstellar objects were not rare cosmic flukes, but regular travelers passing through the Sun's neighborhood. The lessons drawn from Atlas reshaped mission planning, observation networks, and even the global scientific mindset toward the deep unknown. The most immediate shift came in detection infrastructure. The twin Atlas telescopes that had discovered the object in 2024 were upgraded and joined by a network of 12 additional wide-field survey systems strategically distributed across both hemispheres. By 2032, these observatories operated under a unified platform known as the Interstellar Early Warning Array, IEWA. It could automatically triangulate the trajectory of fast-moving objects within hours of detection, predicting their inbound path long before they neared the inner solar system. "Our goal," said Dr. Karen Meach, now chair of the IAU Interstellar Task Group, is to never again meet a visitor by surprise. The Vera C. Rubin Observatory, central to 3 iAtlas's monitoring, also evolved. Its nightly sky survey cadence was doubled, and a new algorithm called Atlas Track, trained on a decade of historical interstellar data, allowed instant identification of hyperbolic trajectories. In 2033, the system successfully flagged a faint, inbound body only 36 hours after its first appearance. Although the object proved to be a dormant long-period comet, the alert demonstrated that humanity was now equipped to detect a 3 I-class visitor weeks earlier than before. In parallel, mission engineers advanced their own form of vigilance. The Interstellar Object Rapid Response Mission, IORM, first conceived after 3 iAtlas's post-Perihelion anomalies, became operational in 2034. A compact solar electric craft stationed near Earth Cell 2 Point, it was capable of leaving orbit within days of an alert. Designed by an international consortium, IORM carried miniature dust analyzers, infrared spectrometers, and a deployable swarm of nanosatellites that could surround a target for close-up imaging. The mission's director, Sarah Coleman, credited Atlas for the design philosophy. "We built for adaptability because that's what Atlas taught us: expect the unexpected." The next transformation occurred at the data level. After 3 iAtlas, astronomical archives were no longer siloed by agency or country. Instead, they were linked through a real-time network called Galactic Net, developed jointly by NASA, ESA, and Japan's NAOJ. The system allowed observatories from Chile to Hawaii to share photometric data instantly, automatically flagging potential interstellar candidates. Artificial intelligence handled pattern recognition, but the classification parameters, reflectivity ratios, acceleration profiles, and volatile spectra were all derived from 3.1 Atlas's dataset. "Its fingerprint became our filter," noted Dr. Miguel de Leon of the European Southern Observatory. Perhaps the most striking legacy was philosophical. Before Atlas, comets were viewed as time capsules of the solar system's own history. After Atlas, they were seen as messengers from other suns, evidence that planetary formation and destruction are universal. Its strange chemistry, rich in carbon monoxide, but poor in water-expanded models of planetesimal formation to include colder, more distant regions of galactic molecular clouds. "We realized," said astrochemist Laura Vance, "that every interstellar object carries a signature of a different cosmic nursery. Studying them is like reading the galaxy's autobiography, one fragment at a time." These revelations also influenced future exploration. When the interstellar probe concept, originally proposed in the 2022, was revived in 2035, its design incorporated lessons from 3.1 Atlas's crossing of the heliopause. The new mission, slated for the late 2030, would not only map the interstellar medium, but also deploy autonomous drones to intercept passing bodies. Each drone, powered by miniaturized ion thrusters, could analyze dust trails in situ and transmit composition data back across the heliosphere. It was an ambitious leap, the direct scientific descendant of Atlas's legacy. Meanwhile, education and research followed suit. By 2036, at least a dozen universities offered interstellar object dynamics programs, blending astrophysics, plasma physics, and planetary geology. The field grew rapidly, with new subdisciplines like heliospheric transition modeling and galactic dust chronology. Much of their foundational literature traced back to the same sources. Meach's 2026 paper on 3 iAtlas's coma persistence, Agarwal's 2028 models of delayed sublimation, and the 2030 Heliopause Crossing Report, authored by NASA and ESA. What began as a single anomaly had become an academic cornerstone. By 2037, the combined observatories of the E1 network detected another hyperbolic intruder, designated 4I, Hesperus travelling at 31 kilometers per second. Unlike Atlas, it showed no visible outgassing, but reflected light with a reddish hue consistent with organic-rich material. IRM launched within 48 hours and intercepted it months later near Jupiter's orbit. Its instruments confirmed nitrogen-bearing hydrocarbons similar to those found in 3I Atlas's tail. For scientists, this marked full-circle validation. Not only was Atlas's chemistry real, but it might be common. The galaxy, said Meach during the mission press briefing, is speaking in the same chemical language everywhere we look. The story of 3I Atlas did not end at the heliopause. It became the foundation for an entire observational strategy spanning decades. It redefined how humanity studies transient celestial events, not as isolated curiosities, but as data-rich encounters linking worlds and stars. Every new comet, every faint dot on a wide-field survey was now examined through the lens that Atlas had shaped. And somewhere far beyond the reach of any instrument, 3I Atlas still moves its ices silent, its dust dispersed, its journey unending. But the path it left through human science remains bright, a trail of observation, collaboration, and curiosity stretching from the volcanic peaks of Mauna Kea to the edge of interstellar space. The comet's physical trace may have vanished, but its influence endures proof that even a fading traveller can change the direction of an entire civilization's gaze. Echoes beyond the boundary, listening for 3I Atlas in the galactic sea. By 2038, 3I Atlas had been gone for 8 years, its faint trace long vanished from telescopic view, its orbit extending into the vast unlit gulf beyond the heliopause. Yet for radio astronomers, the story hadn't ended. The question that lingered across observatories worldwide was simple. Could its presence still be heard? Even if its nucleus was inert, might its charged trail or residual particles continue to interact with the interstellar magnetic field? That question ignited a new phase of investigation, one that pushed listening farther than seeing ever could. The effort began at the Square Kilometre Array, SKA, in South Africa and Western Australia, then the most sensitive radio instrument on Earth. By early 2038, it was already mapping faint galactic emissions from molecular clouds, thousands of light-years away. But a small team led by Dr. Jean-Yves Chauffret proposed something more delicate, to repurpose a segment of the array to monitor the region where 3I, Atlas, had last been tracked. Their goal was to listen for narrowband disturbances, small, coherent fluctuations caused when charged dust grains interact with local interstellar plasma. It's like trying to hear the echo of a single snowflake hitting a window in a storm, Chauffret said. For months, the team collected terabytes of data, filtering out noise from pulsars, quasars, and cosmic background radiation. Finally, in July 2038, they found something repeating microsecond radio pulses occurring roughly every 4.2 hours. The signal was faint, non-periodic, and localized to a small region centered on 3I Atlas's projected trajectory. At first, the group suspected instrumental interference, but after independent confirmation from the 500-meter aperture spherical telescope FAST in China, the anomaly held. The source wasn't artificial, it was plasma turbulence. In essence, the interstellar medium was still responding to the comet's passage. Modelling by the Max Planck Institute for Radio Astronomy suggested that 3I Atlas's ionized dust tail, hundreds of millions of kilometers long when it crossed the heliopause, had not completely dispersed. Instead, it had been stretched into a diffuse filament, trapped along interstellar magnetic field lines. As charged particles within it resonated with background plasma waves, they produced faint radio emissions, detectable across light hours of space. The team named the structure the Atlas filament. "It's not a tail anymore," explained researcher Dr. Fabian Kurt. "It's a fingerprint left in the magnetic field itself." To test the theory, NASA's Interstellar Mapping and Acceleration Probe, IMAP, launched in 2035, turned its sensors toward the same region. IMAP's instruments, designed to detect energetic neutral atoms, ENAs, recorded a subtle gradient in particle density, consistent with residual dust interacting with galactic plasma flow. The signal was weak, but statistically valid. "It's the faintest interaction we've ever measured," said IMAP lead scientist Nikki Fox. "But it means the solar system still remembers where Atlas left." The discovery had far-reaching implications. For decades, astrophysicists had modeled interstellar dust as transient and homogeneous. The Atlas filament suggested otherwise, that interstellar space could retain structured traces of passing bodies for years or even centuries. Each visitor might leave behind a magnetic wake, carrying the memory of its trajectory long after it vanished. "The galaxy could be full of these invisible signatures," said Chauffret. "We just never had ears sensitive enough to hear them." By 2039, radio observatories across the globe joined the search. Japan's Yasuda Deep Space Center, the Allen Telescope Array in California, and France's Nancy Radio Observatory all reported similar detections, irregular but consistent wave modulations echoing through the same coordinates. Cross-correlation analysis confirmed that the disturbances moved slowly relative to background plasma flow, suggesting that they were embedded structures drifting outward from the heliopause. The Atlas filament, now officially catalogued as IF20383I, became the first recorded example of interstellar debris interacting with both heliospheric and galactic fields. The implications went beyond cometary science. In the broader field of heliophysics, it provided direct evidence that the Sun's magnetic influence extends farther and lasts longer than previously believed. Each interaction with an outbound object like 3I Atlas effectively stretched the heliopause, leaving tendrils of charged material suspended in interstellar space. When those tendrils later reconnected with the solar magnetic cycle, they produced faint plasma ripples that spacecraft like Voyager 2 could still detect decades later. "The heliosphere breathes in waves, and 3I Atlas became part of that rhythm," remarked solar physicist Dr. Eleanor Singh. To visualize the phenomenon, the European Space Agency's Gaia Observatory mapped the surrounding stellar region using its high-precision astrometry. When researchers overlaid the SKA radio data on Gaia's positional grid, they found that the Atlas filament aligned almost perfectly with the local magnetic vector pointing toward the star Epsilon Eridani. This alignment suggested that the comet's original interstellar path and its current drift shared a magnetic ancestry. "It's poetic," said Dr. Meach. "We're tracing a line of force that may connect two suns." By late 2039, the detection effort became a coordinated global campaign called Project Resonance, involving more than 40 institutions. Its mandate was to identify similar filaments left by other interstellar visitors. Within months, the project catalogued 2 more candidates, one potentially associated with 2I Borisov's 2019 trajectory. Each discovery strengthened the hypothesis that interstellar objects do not simply pass through, they imprint the galaxy with subtle electromagnetic fingerprints that can persist for decades. Though the signals from the Atlas filament eventually faded below measurable levels by 2040, the effort had proven something fundamental. Interstellar exploration didn't end when an object disappeared. It continued through the space it disturbed, through the invisible ripples it left behind. 3I Atlas had long since moved beyond any instrument's reach, but its echo translated through plasma, magnetism, and data remained the first true sound humanity ever recorded from the galactic sea. And as new instruments turned toward the next faint visitor, one truth endured. Even in silence, the universe speaks to those patient enough to listen. The fourth visitor, How 4I Hesperus, confirmed the Atlas hypothesis. When 4I Hesperus entered the field of view in mid-2037, astronomers recognized the familiar pattern immediately: a faint, fast-moving point of light with a hyperbolic orbit and a speed too high to belong to the Sunday, the Vera C. Rubin. Observatory flagged it first, detecting its trajectory near the constellation Ophiuchus. Within hours, telescopes in Hawaii, Chile, and Spain confirmed the find. A press release followed the next morning. A new interstellar visitor has entered the solar system. Yet beneath the excitement lay a deeper scientific motive: to test whether the strange behaviors of 3I Atlas were unique or part of a larger galactic pattern. The new object, soon designated 4I Hesperus, moved at 31 kilometers per second and followed a steep 38 degrees inclination relative to the ecliptic. Its discovery was no accident. Since the Atlas era, the Interstellar Early Warning Array, IEWA, had been operating continuously, scanning for hyperbolic trajectories. The system's early detection allowed the Interstellar Object Rapid Response Mission, IRM, already stationed at Earth's L2 point, to launch just 4 days later. By late 2038, it was intercepting the inbound body near the orbit of Jupiter. For the first time in history, a spacecraft met an interstellar object while it was still active. The first data from IORM stunned mission control. Hesperus showed no visible coma or tail, yet its reflectivity varied cyclically, implying a slowly rotating, irregular body. Spectrometers revealed a dark, reddish surface, more similar to carbonaceous asteroids than icy comets. It looked inert, said mission scientist Sarah Coleman, but the chemistry told another story. The near-infrared spectra contained sharp absorption features at 3.4 and 4.2 microns, consistent with nitrogen-bearing hydrocarbons and acetylene organic materials remarkably similar to those seen in the fading coma of 3I Atlas. The resemblance was too strong to ignore. To verify the connection, ground-based observatories conducted parallel measurements. The James Webb Space Telescope detected faint emissions from frozen carbon monoxide and methanol volatiles that could sublimate only at moderate solar distances. That meant Hesperus, though visually dormant, was still active beneath the surface. The ratio of carbon monoxide to water was roughly 5:1, nearly identical to Atlas's. It's the same chemical fingerprint, confirmed astronomist Dr. Ayumi Sato. We're seeing the same type of object born cold, shaped far from its star. This parallel extended beyond chemistry. Both interstellar comets showed evidence of delayed outgassing, with internal volatiles venting long after perihelion. IRM's instruments detected microjets on the night side of Hesperus, weak but regular, driven by heat stored deep within the nucleus. The jets rotated in a synchronized rhythm with its 9-hour spin, just as Atlas had displayed periodic flaring years earlier. The behavior is almost one-to-one, said NASA's Lindley Johnson. It's proof that Atlas wasn't a cosmic exception, it was our first example of a broader class. The mission also confirmed the Atlas hypothesis, first proposed in 2028, that interstellar objects can retain internal heat for extended periods due to porous, low-conductivity structures. Hesperus provided direct measurement of that effect. Using thermal radiometers, IORM mapped temperature gradients across its surface. Even on the shaded hemisphere, the temperature remained nearly 20 Kelvin higher than expected, implying that heat from previous solar exposure was slowly migrating inward, sustaining chemical reactions. This discovery validated a key insight from the Atlas observations that interstellar bodies may evolve internally long after external activity ceases. Further support came from isotopic data. The spacecraft's onboard dust analyzer captured several microparticles ejected by weak jets. Laboratory-style analysis, performed remotely, showed carbon isotope ratios 13C, 12C, 8% higher than the solar standard, the same anomaly recorded in Atlas's dust samples years earlier. The likelihood of coincidence was statistically negligible. Two independent visitors, the same isotopic signature, noted Dr. Karen Meach. It's the first real evidence that we're sampling matter from a shared stellar nursery somewhere beyond our system. The discovery also strengthened a growing model of galactic material circulation. Both Atlas and Hesperus exhibited trajectories tracing back toward the same region of local interstellar space. Near the Epsilon Eridani stream, a known corridor of gas and dust, connecting nearby star-forming regions. When ESA's Gaia mission reconstructed their inbound vectors, the overlap was unmistakable. It's as if the galaxy itself sent two emissaries from the same place, said European Space Operations Center analyst Miguel de Leon. That's not coincidence, it's galactic architecture. Throughout 2039, IRM continued close observation, gradually trailing Hesperus as it swung around the Sun and began its outbound journey. Unlike Atlas, it didn't fragment or flare dramatically. Its brightness declined steadily, its color shifted from red to near-neutral gray, and its faint jets subsided into silence. But even as it faded, the data kept matching Atlas's patterns. Subsurface crystallization, volatile release, minor acceleration, all the same physical language, repeated with minor variations. By the time the spacecraft ended its mission in 2040, scientists no longer doubted the connection. The Atlas hypothesis had become established fact. In 2041, the Journal of Interstellar Science published a landmark paper summarizing 5 years of observation. Its title was simple: Comparative Composition and Dynamics of 3T Atlas and 4I Hesperus. The findings confirmed that both objects likely originated from a low metallicity stellar environment, rich in carbon and nitrogen but depleted in oxygen. The conclusion was profound. Many interstellar comets are not icy remnants of distant suns, but fragments from the cold outer regions of protoplanetary disks around small, long-lived stars. For planetary scientists, the implications reached beyond curiosity. It meant that material from other solar systems routinely crosses ours, carrying the chemical fingerprints of distant star nurseries. For exoplanet researchers, it provided physical samples of other worlds' building blocks without the need to leave our own. It's the galaxy delivering geology to our doorstep, said ESA Director Jean-Luc Besson during the IRM mission debrief. By the mid-2040s, the lesson was clear. 3. I-Atlas had not been a singular anomaly, but the first known member of a family of slow-evolving interstellar comets' bodies capable of storing energy, releasing gas, and altering their motion long after leaving their parent stars. Hesperus had confirmed it empirically, closing one of the most enduring questions of 21st century astronomy. And as both objects drifted into the infinite dark, separated by billions of kilometers but bound by shared origin, humanity's understanding of the cosmos expanded one step farther from seeing the galaxy as distant and abstract to realizing that fragments of its farthest corners had already passed among us. The interstellar network, humanity's new era of deep space listening. By 2042, astronomy no longer relied solely on telescopes. It had become a discipline of listening, a global orchestration of instruments, spacecraft, and algorithms linked through an invisible web that spanned from the deserts of Chile to the outer edge of the solar system. This system, born directly from the discoveries surrounding 3.1 Atlas and 4I Hesperus, was known simply as the Interstellar Network, a planet-sized array designed to detect, trace, and study every fragment of matter crossing between stars. The idea originated after the confirmation of the Atlas filament in 2039. Scientists realized that the galaxy was threaded with faint electromagnetic scars, left by passing objects' trails of charged particles and plasma disturbances that could persist for decades. To map them, no single observatory would suffice. A network of synchronized receivers, spread across Earth and space, would be required to capture the entire chorus of interstellar motion. The first phase began with upgrades to the Square Kilometre Array, SKA, in South Africa and Australia. By linking its low and mid-frequency antennas through real-time quantum communication channels, researchers created an unprecedented dynamic baseline capable of resolving microhertz-level fluctuations in deep space plasma. The array was then connected to ALMA in Chile, FAST in China, and the newly built Mauna Kea interstellar listening post in Hawaii. Together, they formed a global aperture thousands of kilometers wide, capable of detecting plasma waves weaker than a whisper from across the galaxy. The second phase extended the network into space. NASA repurposed Voyager 2 and New Horizons as passive outposts, updating their firmware to allow data relaying via the Deep Space Network. The European Space Agency launched two specialized relay probes, Echo 1 and Echo 2, placed at the solar gravitational lens focus, nearly 550 astronomical units away. Their job was to amplify faint interstellar radio emissions that bent around the Sun's gravity, turning our star into a natural cosmic microphone. "We built antennas in orbit," said ESA engineer Jean-Yves Chauffret, "and the Sun became the dish." By 2044, the system's first unified test began. The target was the region once traversed by 3I Atlas, where remnants of its plasma filament had last been measured years earlier. The synchronized network recorded a low-frequency hum, a coherent electromagnetic resonance that fluctuated with the solar cycle. Cross-correlation confirmed it matched the magnetic topology left by the Atlas filament. It was faint, almost gone, but undeniably there. "It's the galaxy breathing," said SKA project scientist Dr. Eleanor Singh. "We're hearing how the stars themselves communicate through the dust between them." But the network's true triumph came later that year, when it detected a completely new signature, a fast-moving magnetic disturbance entering the solar system from the direction of the constellation Lyra. The data didn't match solar wind patterns or cosmic rays. Within hours, Iowa's optical telescopes confirmed the cause. A new interstellar object, soon designated 5I Lyra. The detection had occurred more than 6 weeks before the body became optically visible. For the first time in human history, a visitor from another star had been discovered by its wake in interstellar plasma rather than its reflected light. That moment defined the interstellar network's success. Astronomers called it the Atlas effect, the ability to sense an object before it could be seen, made possible by the understanding gained from 3I Atlas's lingering electromagnetic trace. "It was the comet that taught us to listen first and look second," said NASA physicist Sarah Coleman. The detection led to a rapid response. The Interstellar Object Rapid Response Mission, IRM-2, launched in 2043, altered its trajectory toward Lyra within days of confirmation. The mission's intercept was achieved at record speed, guided entirely by the network's continuous plasma mapping rather than visual tracking. As one scientist described it, "We were following its song, not its shadow." Beyond discovery, the network changed how scientists viewed the Milky Way itself, 3I Atlas, and its successors had shown that the galaxy isn't empty between stars. It's threaded with faint, interconnected highways of material and energy. By 2045, the interstellar network had mapped more than 40 of these structures, identifying potential pathways where dust, gas, and small bodies drifted between stellar systems. Some extended for light years, looping around clusters like magnetic rivers. The Milky Way is porous, said theoretical physicist Dr. Ayumi Sato. The same forces that carried Atlas to us are still flowing, an ongoing exchange of matter linking the galaxy together. As the network matured, artificial intelligence became its interpreter. Quantum processors analyzed thousands of terabytes daily, flagging transient distortions for human review. Patterns once dismissed as noise were reclassified as meaningful signals, slow modulations hinting at distant collisions, or resonant waves left by long-vanished bodies. Every week, new data emerged showing how the Sun's magnetic field connected with the galaxy's broader web. By 2046, the interstellar network had grown to include deep space assets from India, Canada, Brazil, and the UAE, making it one of the largest scientific collaborations ever assembled. Its continuous coverage allowed not only the early discovery of interstellar visitors, but also the monitoring of how they interact with the solar boundary. The heliopause, once seen as a static barrier, was now understood as a living interface that flexed and rippled in response to these crossings. The final confirmation of the network's power came during the monitoring of 5I, Lyra's departure in 2047. As the object approached the heliopause, the combined data from Echo 2 and SKA captured the faint resonance of its magnetic interaction, a rising hum, identical in profile to what had been recorded when 3I Atlas left 17 years earlier. The pattern was unmistakable. It was the same voice, said Chauffret, the same type of object leaving the same kind of footprint, only now we were listening on purpose. The interstellar network had closed a circle that began with confusion and ended in comprehension. What once seemed like random cosmic intrusions were now understood as part of the galaxy's continuous dialogue, the whisper of stars exchanging fragments through space. And though each new object came from a different origin, their collective story pointed to a single truth. The Milky Way was not a collection of isolated suns, but a connected ecosystem of worlds, linked by the faint trails of wanderers like 3I Atlas. For humanity, the act of listening had become the greatest scientific instrument of all, one that began, fittingly, with a single question asked decades earlier in the quiet data of a fading comet. What else is out there, waiting to be heard? Space. Near the Epsilon Eridani stream, a known corridor of gas and dust connecting nearby star-forming regions. When ESA's Gaia mission reconstructed their inbound vectors, the overlap was unmistakable. It's as if the galaxy itself sent two emissaries from the same place, said European Space Operations Center analyst Miguel de Leon. That's not coincidence, it's galactic architecture. Throughout 2039, IRM continued close observation, gradually trailing Hesperus as it swung around the Sun and began its outbound journey. Unlike Atlas, it didn't fragment or flare dramatically. Its brightness declined steadily, its color shifted from red to near-neutral gray, and its faint jets subsided into silence. But even as it faded, the data kept matching Atlas's patterns. Subsurface crystallization, volatile release, minor acceleration, all the same physical language, repeated with minor variations. By the time the spacecraft ended its mission in 2040, scientists no longer doubted the connection. The Atlas hypothesis had become established fact. In 2041, the Journal of Interstellar Science published a landmark paper summarizing 5 years of observation. Its title was simple: Comparative Composition and Dynamics of 3I Atlas and 4I Hesperus. The findings confirmed that both objects likely originated from a low metallicity stellar environment, rich in carbon and nitrogen, but depleted in oxygen. The conclusion was profound. Many interstellar comets are not icy remnants of distant suns, but fragments from the cold outer regions of protoplanetary disks around small, long-lived stars. For planetary scientists, the implications reached beyond curiosity. It meant that material from other solar systems routinely crosses ours, carrying the chemical fingerprints of distant star nurseries. For exoplanet researchers, it provided physical samples of other worlds' building blocks without the need to leave our own. "It's the galaxy delivering geology to our doorstep," said ESA director Jean-Luc Besson during the IRM mission debrief. By the mid-2040s, the lesson was clear. 3I Atlas had not been a singular anomaly, but the first known member of a family of slow-evolving interstellar comets bodies capable of storing energy, releasing gas, and altering their motion long after leaving their parent stars. Hesperus had confirmed it empirically, closing one of the most enduring questions of 21st century astronomy. And as both objects drifted into the infinite dark, separated by billions of kilometers, but bound by shared origin, humanity's understanding of the cosmos expanded one step farther from seeing the galaxy as distant and abstract to realizing that fragments of its farthest corners had already passed among us. The interstellar network, humanity's new era of deep space listening. By 2042, astronomy no longer relied solely on telescopes. It had become a discipline of listening, a global orchestration of instruments, spacecraft, and algorithms, linked through an invisible web that spanned from the deserts of Chile to the outer edge of the solar system. This system, born directly from the discoveries surrounding 3I Atlas and 4I Hesperus, was known simply as the Interstellar Network, a planet-sized array designed to detect, trace, and study every fragment of matter crossing between stars. The idea originated after the confirmation of the Atlas filament in 2039. Scientists realized that the galaxy was threaded with faint electromagnetic scars, left by passing objects' trails of charged particles and plasma disturbances that could persist for decades. To map them, no single observatory would suffice. A network of synchronized receivers spread across Earth and space would be required to capture the entire chorus of interstellar motion. The first phase began with upgrades to the Square Kilometre Array, SKA, in South Africa and Australia. By linking its low and mid-frequency antennas through real-time quantum communication channels, researchers created an unprecedented dynamic baseline capable of resolving microhertz-level fluctuations in deep space plasma. The array was then connected to ALMA in Chile, FAST in China, and the newly built Mauna Kea interstellar listening post in Hawaii. Together, they formed a global aperture thousands of kilometers wide, capable of detecting plasma waves weaker than a whisper from across the galaxy. The second phase extended the network into space. NASA repurposed Voyager 2 and New Horizons as passive outposts, updating their firmware to allow data relaying via the Deep Space Network. The European Space Agency launched two specialized relay probes, ECHO 1 and ECHO 2, placed at the solar gravitational lens focus, nearly 550 astronomical units away. Their job was to amplify faint interstellar radio emissions that bent around the sun's gravity, turning our star into a natural cosmic microphone. "We built antennas in orbit," said ESA engineer Jean-Yves Chauffret, "and the sun became the dish." By 2044, the system's first unified test began. The target was the region once traversed by 3I Atlas, where remnants of its plasma filament had last been measured years earlier. The synchronized network recorded a low-frequency hum, a coherent electromagnetic resonance that fluctuated with the solar cycle. Cross-correlation confirmed it matched the magnetic topology left by the Atlas filament. It was faint, almost gone, but undeniably there. "It's the galaxy breathing," said SKA project scientist Dr. Eleanor Singh. "We're hearing how the stars themselves communicate through the dust between them." But the network's true triumph came later that year, when it detected a completely new signature, a fast-moving magnetic disturbance entering the solar system from the direction of the constellation Lyra. The data didn't match solar wind patterns or cosmic rays. Within hours, Iowa's optical telescopes confirmed the cause, a new interstellar object, soon designated 5I, Lyra. The detection had occurred more than 6 weeks before the body became optically visible. For the first time in human history, a visitor from another star had been discovered by its wake in interstellar plasma rather than its reflected light. That moment defined the interstellar network's success. Astronomers called it the Atlas effect, the ability to sense an object before it could be seen, made possible by the understanding gained from 3I Atlas's lingering electromagnetic trace. "It was the comet that taught us to listen first and look second," said NASA physicist Sarah Coleman. The detection led to a rapid response. The Interstellar Object Rapid Response Mission, IRM-2, launched in 2043, altered its trajectory toward Lyra within days of confirmation. The mission's intercept was achieved at record speed, guided entirely by the network's continuous plasma mapping rather than visual tracking. As one scientist described it, "We were following its song, not its shadow." Beyond discovery, the network changed how scientists viewed the Milky Way itself. 3I Atlas and its successors had shown that the galaxy isn't empty between stars. It's threaded with faint, interconnected highways of material and energy. By 2045, the interstellar network had mapped more than 40 of these structures, identifying potential pathways where dust, gas, and small bodies drifted between stellar systems. Some extended for light years, looping around clusters like magnetic rivers. "The Milky Way is porous," said theoretical physicist Dr. Ayumi Sato. "The same forces that carried Atlas to us are still flowing an ongoing exchange of matter, linking the galaxy together." As the network matured, artificial intelligence became its interpreter. Quantum processors analyzed thousands of terabytes daily, flagging transient distortions for human review. Patterns once dismissed as noise were reclassified as meaningful signals, slow modulations hinting at distant collisions, or resonant waves left by long-vanished bodies. Every week, new data emerged showing how the Sun's magnetic field connected with the galaxy's broader web. By 2046, the interstellar network had grown to include deep space assets from India, Canada, Brazil, and the UAE, making it one of the largest scientific collaborations ever assembled. Its continuous coverage allowed not only the early discovery of interstellar visitors, but also the monitoring of how they interact with the solar boundary. The heliopause, once seen as a static barrier, was now understood as a living interface that flexed and rippled in response to these crossings. The final confirmation of the network's power came during the monitoring of 5I Lyra's departure in 2047. As the object approached the heliopause, the combined data from Echo 2 and SK captured the faint resonance of its magnetic interaction, a rising hum, identical in profile to what had been recorded when 3I Atlas left 17 years earlier. The pattern was unmistakable. "It was the same voice," said Chauffret. "The same type of object leaving the same kind of footprint, only now we were listening on purpose." The interstellar network had closed a circle that began with confusion and ended in comprehension. What once seemed like random cosmic intrusions were now understood as part of the galaxy's continuous dialogue, the whisper of stars exchanging fragments through space. And though each new object came from a different origin, their collective story pointed to a single truth. The Milky Way was not a collection of isolated suns, but a connected ecosystem of worlds, linked by the faint trails of wanderers like 3I Atlas. For humanity, the act of listening had become the greatest scientific instrument of all, one that began, fittingly, with a single question asked decades earlier in the quiet data of a fading comet. What else is out there, waiting to be heard? The Milky Way's hidden highways, mapping the interstellar streams revealed by ATLAS. By 2048, the interstellar network had mapped more than just the echoes of individual comets. It had begun charting the invisible architecture of the Milky Way itself. What the world once imagined as vast emptiness between stars now appeared as a tangled mesh of magnetic filaments, dust rivers, and plasma corridors, gently ferrying material from one stellar system to another. The revelation came directly from data inspired by 3I Atlas. Its faint plasma wake, the first ever recorded, became the model for recognizing similar trails elsewhere, and soon dozens more appeared. The discovery began with a pattern. When researchers overlaid long-term radio and optical observations from the interstellar network, they noticed repeating alignments between the trajectories of 2I Borisov, 3I Atlas, and 4I Hesperus. Though separated by decades, their entry vectors traced back toward the same galactic coordinates near Epsilon Eridani. Statistically, that overlap should have been impossible. Yet simulations from the Max Planck Institute's Galactic Dynamics Division confirmed it wasn't coincidence, it was structure. The objects had likely travelled along the same interstellar stream, a slow-moving current of gas and dust shaped by magnetic fields that arced through the local bubble of the Milky Way. To study it, the interstellar network deployed its most advanced phase yet, Project Streamline, a coordinated effort between NASA, ESA, and JAXA. Using the SKA's full aperture, in combination with ESA's Gaia astrometry data, the team mapped plasma density across the local interstellar medium. The results were astonishing. Between the Sun and the nearby star, Tau Ceti stretched a continuous filament, nearly 3 light-years long, composed of charged dust grains, aligned by galactic magnetic fields. When plotted in 3 dimensions, the structure looked like a river, thin, branching, and dynamic. "These are not random voids filled with debris," said Dr. Eleanor Singh, lead scientist for Project Streamline. "They're highways of matter, shaped by magnetism and motion, connecting stellar neighborhoods across the galaxy." Further analysis revealed that the Epsilon Eridani stream, the very corridor believed to have carried 3I Atlas, was one of several such routes passing through the solar system's vicinity. Each stream exhibited unique composition signatures, defined by the ratio of carbon, nitrogen, and silicate dust. In one, the dominant particles matched the isotopic patterns of Hesperus. In another, the ratios aligned more closely with 2I, Borisov. Together, these discoveries painted a vivid picture. Our solar system wasn't an isolated bubble, but a temporary waypoint in a vast, flowing system of interstellar exchange. By 2049, computer models using interstellar network data produced the first 3-dimensional galactic traffic map, a visualization of how matter migrates between stars over millions of years. The streams curved and coiled, weaving through regions of stronger magnetic flux like roads through mountainous terrain. Some converged in dense hubs near star-forming regions, others extended outward, fading into the interarm voids. "It's like discovering the ocean currents of the Milky Way," said ESA researcher Dr. Ayumi Sato. "They shape how dust, gas, and even potential life-bearing molecules move from one system to another." The implications were profound. For astrobiology, the discovery revived the long-standing idea of panspermia, the hypothesis that microbial life, or at least its chemical precursors, can travel between worlds. If solid material could drift along these stable magnetic paths for millions of years, then planetary systems were not isolated experiments, but participants in a shared galactic cycle of chemistry. As Dr. Karen Meach summarized in a 2049 symposium, "We no longer ask whether life could arise independently elsewhere. We ask how far it's already traveled." On a practical level, mapping these streams also changed how space agencies planned interstellar missions. Instead of propelling future probes directly into the void, engineers began designing trajectories that would align with natural magnetic corridors, allowing spacecraft to sail with reduced energy expenditure. The first of these, the Magellan Interstellar Pathfinder, was scheduled for launch in 2052, set to follow the Epsilon Eridani stream outbound for several light months. Its purpose: to confirm the composition and flow rate of the very channel that once carried 3I Atlas. Meanwhile, data from ESA's ECO-2 and NASA's IMAP provided confirmation that the heliosphere itself was being stretched and shaped by these galactic rivers. The Sun, moving through the interstellar medium at 26 kilometers per second, constantly drifted in and out of these magnetic channels. Each passage subtly altered the heliopore's density and magnetic orientation, producing fluctuations that the interstellar network could now measure in real time. For the first time, scientists saw the solar system not as a static bubble, but as a vessel sailing through a dynamic sea. By late 2050, the interstellar network had identified at least 12 distinct galactic highways within 20 light-years of Earth. Some originated near star-forming regions such as Epsilon Eridani and Tau Ceti. Others extended from ancient stellar remnants, carrying mineral-rich debris from long-dead worlds. One particularly large structure, dubbed the Perseus Arm Stream, appeared to channel material from hundreds of light-years away, its currents faint but traceable through polarized radio emissions. The unifying discovery behind them all was that their structure and their visibility could be traced back to the first interstellar wake humanity ever detected. 3I Atlas's faint, vanishing tail. Its anomalies, once dismissed as irregularities, became the foundation for a galactic cartography that had never existed before. Atlas didn't just show us another comet, said Dr. Miguel de Leon at the International Astronomical Union's centennial meeting. It showed us the river it came from. By 2051, entire databases were devoted to tracking and modeling these flows, collectively known as the Atlas Grid. It combined plasma, dust, and isotopic data into a continuously updating simulation of interstellar circulation. Researchers used it to predict where the next visitors might appear and how their compositions would differ. The once random arrivals of objects like 1I Oumuamua and 2I Borisov now fit neatly into mapped trajectories. The galaxy, it seemed, followed routes as structured as any weather system on Earth. In the quiet halls of observatories, amid the hum of data servers and the low static of the cosmic background, scientists found themselves returning to a familiar thought that all of this began with a single, dim object briefly visible through a Hawaiian telescope in 2024. 3I Atlas had been the first to hint that the universe's silence was not emptiness, but motion. And as the Atlas Grid continued to expand, tracing more and more of the Milky Way's hidden pathways, a new philosophy took hold in astronomy. That space itself was not static, but living a circulation of stars, matter, and memory. Each new visitor was no longer a mystery intruder, but a traveler following ancient routes that had always been there, waiting to be mapped. Interstellar origins, tracing Atlas back to its home star system. By the early 2052, nearly 3 decades after its discovery, 3I Atlas had transitioned from a mysterious comet into a cosmic breadcrumb, the first tangible clue in humanity's quest to trace an interstellar object back to its origin star. Ever since the final trajectory data was archived, astrophysicists across the world had worked toward one impossible-sounding question: where did it come from? The task began with backward modeling. Using orbital data collected between 2024 and 2029, scientists reconstructed 3I Atlas's inbound vector line through space, defined by its hyperbolic excess velocity of 31.9 kilometers per second, and its inclination of roughly 40 degrees relative to the ecliptic. Over time, gravitational encounters with the outer planets, solar radiation pressure, and non-gravitational outgassing had all slightly altered this path, but advanced corrections derived from the Atlas grid and interstellar network allowed researchers to reverse those effects with unprecedented accuracy. By 2049, the Max Planck Institute for Astronomy, working with NASA's Jet Propulsion Laboratory, had extended the model backward across 50,000 years of galactic motion, accounting for the Sun's trajectory through the local interstellar cloud. The line intersected a region of space near Epsilon Eridani, just 12 light-years away. Long suspected of being part of the same dust current that carried Atlas and Hesperus, Epsilon Eridani was a young, active K-type star surrounded by a dense debris disk, a stellar nursery in miniature. It's exactly the kind of system that would produce icy planetesimals capable of surviving interstellar travel, said project lead Dr. Rainer Kresak. But confirmation required more than orbital geometry. Astronomers turned to spectral fingerprinting, comparing the isotopic ratios of carbon, nitrogen, and oxygen in Atlas's ejecta to those observed in nearby star systems. The data, captured decades earlier by James Webb and ALMA, had been preserved in digital archives. When matched against emission spectra from Epsilon Eridani's protoplanetary debris disk, the similarity was striking. Both exhibited elevated 13C, 12C ratios and depleted 18O-16O levels, along with unusual abundances of nitrile-bearing hydrocarbons. It's not proof, cautioned astrochemist Dr. Ayumi Sato, but it's a fingerprint match within 2 sigma. Statistically, that's very close to saying it came from there. The next breakthrough came from the Gaia mission's extended dataset. By mapping stellar motions backward in time, Gaia's 4th data release reconstructed how Epsilon Eridani and the Sun approached one another roughly 900,000 years ago. At that time, the two systems had passed within 2.3 light-years, close enough for gravitational perturbations to nudge debris from Epsilon Eridani's outer disk into interstellar space. That's our launch event, said ESA analyst Dr. Miguel de Leon. It's entirely plausible that 3I Atlas was ejected during that encounter, beginning a million-year journey that ended in our solar system. To test the hypothesis, the interstellar network coordinated a massive simulation using its combined computing power across Earth and orbital data centers. It modeled particle ejections from Epsilon Eridani's disk over the last million years, tracing which fragments could have followed trajectories consistent with Atlas's inbound path. Out of 10 million virtual bodies, 127 matched both speed and direction within acceptable tolerances. Each one represented a potential origin scenario. The most likely cause, gravitational scattering by one of Epsilon Eridani's known giant planets, an analogue to Jupiter, sending icy debris beyond the system's escape velocity. Once adrift, the fragments would have followed the galactic magnetic current now known as the Epsilon Eridani stream, the same route that later delivered Hesperus. Over time, collisions with interstellar dust and radiation gradually modified their surfaces, producing the dark organic crust and volatile rich interior seen in both comets. The consistency between chemical and dynamic evidence is remarkable, said NASA's Lindley Johnson. For the first time, we can name a probable birthplace for an interstellar object. Still, scientists sought an independent line of verification. In 2050, the Magellan Interstellar Pathfinder, en route to the outer solar system, deployed an experimental dust collector along the predicted flow of the Epsilon Eridani stream. Within a year, it captured several microscopic grains, whose isotopic composition perfectly matched Atlas's archive samples. The discovery, announced in 2051, effectively confirmed the link. "We're holding pieces of the same cloud that birthed our first interstellar visitor," said mission scientist Eleanor Singh. "It's like finding a fossil from the same geological layer, only the rock is 1 million years old and from another star." The result rippled through every branch of astrophysics. For planetary formation theorists, it proved that interstellar transport of solid material is not rare. It's a natural outcome of gravitational interactions between young stars. For astrobiologists, it meant that organic molecules could survive journeys between stellar systems intact. And for galactic dynamicists, it revealed that local stars are not isolated, but constantly exchanging matter along magnetic and gravitational corridors. In 2052, NASA, ESA, and JAXA published the landmark Interstellar Provenance Report, summarizing 20 years of investigation. Its final statement read, "Is greater than, based on orbital reconstruction, isotopic correlation, and galactic motion modeling, the object known as 3I, Atlas, most likely originated from the Epsilon Eridani debris disk, approximately 900,000 plus or minus 150,000 years ago." The conclusion was cautious but monumental. For the first time in human history, scientists had traced a single object across interstellar space back to its home system, an act of cosmic archaeology on a galactic scale. The data offered not just a story of motion, but of continuity. A fragment born around another sun had crossed the gulf of stars, touched our world's sky, and then continued onward, leaving behind knowledge instead of dust. In an address at the International Astronomical Union's 2052 summit, Dr. Meach reflected on the journey that began nearly 30 years earlier. Atlas came from a sun not so different from ours. It carried within it the chemistry of a young system, the silence of deep space, and the memory of its ejection. We followed its trail backward and found that the universe isn't random at all. It's threaded with connection. 3I, Atlas didn't just visit us. It came home through understanding. The realization changed the way humanity viewed interstellar space. It was no longer a void separating stars, but a continuum, linking them, a bridge of drifting matter where every comet, dust grain, and filament carried a trace of its origin. And as telescopes turned once more toward Epsilon Eridani, the question shifted from where did it come from to how many more are on their way. The galactic exchange. How Atlas redefined the life cycle of stars and worlds. By 2053, the legacy of 3I Atlas had evolved beyond cometary science. What began as a faint, icy visitor had grown into a unifying framework explaining how stars, planets, and organic matter are continually recycled across the Milky Way. Astronomers began calling this concept the galactic exchange, the idea that stellar systems are not isolated laboratories of evolution, but open participants in a cosmic economy of material transfer. And at the center of that realization stood Atlas, the first object to prove the theory with data instead of speculation. The foundations of the galactic exchange were laid during the post-Atlas decade. Studies of isotopic anomalies in interstellar dust, the mapping of magnetic filaments, and the confirmed trajectories of 4.1, Hesperus, and 5.1, Lyra, all pointed to a shared conclusion. The Milky Way actively redistributes its raw materials. Just as Earth's oceans circulate heat and nutrients across the planet, the galaxy circulates atoms, silicates, carbons, ices, and even prebiotic compounds through gravitational scattering and magnetic transport. "We used to think of stars as fixed systems," said Dr. Eleanor Singh of the Interstellar Network. "Now we know they're just nodes in a much larger exchange system." The most compelling evidence came from isotopic modeling. The Atlas grid, continuously updated by data from the Interstellar Network, revealed that the isotopic ratios found in Atlas, Hesperus, and debris within the Epsilon Eridani stream could not have originated from a single stellar generation. Their composition suggested that at least 3 cycles of supernova enrichment and star formation had contributed to the material's makeup. "What we're holding in these interstellar bodies," said Dr. Ayumi Sato, "are records of multiple stellar lives matter that's been reborn more than once." This understanding forced a revision of the traditional stellar life cycle diagram. Once depicted as a closed-loop star formation, planetary formation, stellar death, the new model included branching filaments representing outbound material flows. Some originated from supernova ejecta, others from the gentle scattering of comets and planetesimals. The galaxy, scientists realized, doesn't merely recycle matter within stars, it trades it between them. 3I Atlas was the first physical confirmation of that trade route. The interstellar network's continuous monitoring of dust and plasma now made it possible to quantify the scale of this exchange. By correlating data from radio arrays and spacecraft detectors, researchers estimated that nearly 5% of the material in the solar system may have interstellar origin particles and organics delivered over billions of years through galactic drift. Conversely, simulations predicted that an equivalent fraction of the Sun's own debris has already left to seed other systems. "We're both donor and recipient," explained NASA astrophysicist Miguel de Leon. "Atlas just happened to be one of the shipments coming back through." The discovery redefined theories of planetary chemistry. Laboratory studies using analog samples, including dust captured from the Magellan Interstellar Pathfinder, showed that the organic compounds found in Atlas could act as catalysts in prebiotic reactions at extremely low temperatures. This meant that even before planets formed, the seeds of amino acids and complex carbon chains could already exist, traveling freely between forming systems. "It blurs the line between cosmic and biological evolution," said astrobiologist Dr. Laura Vance. "Life's chemistry might not start in one place. It might simply continue wherever the galaxy carries it." Meanwhile, cosmochemists focused on what Atlas revealed about stellar neighborhoods. By tracing its isotopic profile back through the Epsilon Eridani stream, researchers found correlations with the compositions of nearby systems such as Tau Ceti, 40 Eridani, and Captain's star. Each showed similar chemical imprints, suggesting a shared origin cluster, a region of space that once hosted multiple young stars exchanging debris through mutual gravity. The implication was startling. Many of the local stars, including the Sun, might share fragments of the same primordial material, scattered and mixed across millions of years. In 2055, a landmark paper published in Nature Astronomy formalized these findings. It presented the Atlas model of galactic circulation, which described how interstellar currents, magnetic fields, and stellar encounters maintain continuous mass flow throughout the Milky Way. The model proposed that small bodies, like Atlas, are the galaxy's couriers vehicles of mineral and organic information. Every interstellar comet, the authors wrote, is a messenger carrying samples of ancient worlds, sharing them among stars like pollen across a galactic field. For astrophysicists, the Atlas model transformed long-standing theories about galactic evolution. It suggested that the Milky Way's chemical uniformity, the reason stars within a few thousand light-years share similar elemental ratios, is maintained not only by supernova distribution, but also by cometary transfer. The idea that icy debris could influence galactic-scale composition once seemed unthinkable. But the data, verified through direct observation, left little doubt. The philosophical impact was equally profound. Humanity's understanding of its place in the cosmos shifted from isolation to participation. The realization that our solar system both receives and contributes material to the galaxy redefined notions of cosmic identity. "When we look up now," said Dr. Karen Meach at the 2055 IAU Centennial Congress, "we're not looking out at the unknown. We're looking at parts of ourselves moving through the dark fragments of our atoms traveling outward and fragments of others coming home. By 2056, the Atlas grid had evolved into a predictive tool for identifying future exchange events regions where the sun's motion would intersect with dense interstellar streams. These crossings, once purely academic, now carried practical significance. As space exploration pushed toward the outer solar system, planners accounted for interstellar dust density in navigation models. The next predicted crossing, expected around 2070, was projected to increase inbound dust flow by 15%, potentially offering a new influx of material from other stars. In educational institutions and observatories alike, the story of 3I Atlas became shorthand for the era when astronomy expanded from studying isolated celestial objects to understanding the galaxy as a single, living system. The comet's once mysterious brightness fluctuations, its anomalous acceleration, its post-Perihelion persistence, all the puzzles that had confounded early observers now read like early pages in a cosmic textbook, revealing the interconnected machinery of the Milky Way. And though Atlas itself had long vanished into the galactic night, its presence endured in the data it inspired, the missions it launched, and the philosophy it left behind. It had shown that the matter composing worlds, stars, and perhaps life itself was never fixed, never confined, but always in motion, exchanged, shared, and renewed. As scientists across Earth looked toward the next century of discovery, one quiet truth continued to echo from that single interstellar traveler. Nothing in the universe stands alone. Every atom is a migrant, every orbit a bridge, and every comet like 3I Atlas, a reminder that even across the gulf between stars, the galaxy remembers its own. 3I Atlas vanished decades ago, its light now lost beyond the heliopause, but its legacy endures. From its passing, humanity built the interstellar network, charted the galaxy's hidden highways, and traced its path back to the Epsilon Eridani system. It proved that stars are not isolated, but connected, sharing matter, memory, and chemistry across light years. Every interstellar visitor since has carried a fragment of that same story, that the Milky Way is alive with exchange, and that we are part of it. In the quiet data left behind, 3I Atlas gave us more than measurements, it gave us perspective. It showed that even the smallest wanderer can rewrite the story of an entire galaxy. And as we listen for the next faint traveler crossing the dark, we remember that discovery doesn't end with sight. It begins with attention. Stay curious, stay listening. Join us on the next journey.